Hello, my name's Nigel Griffiths. I work in the Advanced Technology Centre in the UK, part of IBM Europe. In this movie we're going to look at active memory sharing, but before going into the details of that, we're going to look at how regular paging works. And you might ask yourself, why are we doing this? Well, active memory sharing, AMS, is built on top of virtual memory, or the paging system in the AX kernel. And if you don't understand how virtual memory or paging works, well, you better stop now, because you could get into real serious problems with misunderstandings of how paging works when you switch on active memory sharing. So how does virtual memory work? Well, a program thinks it's running in a virtual address space, and it thinks that it is all in memory. But in actual fact, only part of the program is in real memory, held in these tiny 4K memory pages. But a large chunk of the program is not actually in memory, it's actually stored on the disks. Now the reason we do this is because disk space is 1,000 times cheaper than memory. But of course disks are also 1,000 times slower, so we have to move things quickly between the disk and memory to hide the fact that we're actually using the disks for part of the program. Now there's lots of virtual memory benefits and demands, and I'll go through a couple of these. So this explains why we actually want to have this feature. Now it allows us to run very large programs when only a proportion of a program is actually in memory. This means that we can actually start programs far faster. We only have to get a few percent of the program actually in memory before we can actually start executing it. And it also means we can save some money by not buying so much memory. It protects the kernel, the operating system, from user processes, so that the user process is in virtual memory and it can't actually see the physical memory in the machine or make changes to it. It also means user processes can't actually affect each other, so that they don't corrupt each other's data. It also means, as a programmer, every time my program starts, it sees the same virtual address space regardless of where it physically is in memory, and this can make programming easier. Now to get these benefits, we need quite a lot of things for the processor to actually do as features to support virtual memory. First of all, the processor has to understand whether it's in kernel mode, in the operating system, or in the user process. And it does this by a kernel user mode bit. When we're in a user process, there are some instructions that are not allowed, and this allows the kernel to protect itself from rogue user programs. Also, when the processor tries to get access to a virtual address space of a process, it has to be translated into the physical address inside the machine, where it actually is in memory. It does this by using page tables. When a virtual to physical translation fails, we then need the program to be stopped. We get an interrupt, so we jump into kernel mode, we switch the bit, and the kernel then can patch over this problem. It can decide that it was a good piece of virtual memory that you are trying to access, but it's actually on the disk at the moment. It can then quickly read that in from the disk into memory, and then we want the program to go back and restart that instruction, and it should now work, as it will actually find the addresses in memory. And let's have a look at the components that build up the virtual memory and paging subsystem. Now here's our program. It's built out of a number of memory pages, and they have different things in them. For example, it has the code, the actual instructions that it's going to follow. Then it has some data, maybe more than one page. Then we have something called a heap, which is the working storage. It can ask for extra memory to do some manipulation of data. It probably has some libraries attached, so we got some more code and more data. And finally we have a thing called a stack, which is used for calling functions and returning data. Inside the actual machine we have real memory pages in 4K pieces. And these are mapped so that the program is actually mapped into particular memory pages. And unless you're the first program in when the computer starts, you will find that the virtual memory of your program is scattered all across memory inside the machine. There's no laying out of it in a particular order, because it doesn't matter where it is, as long as we can translate your virtual addresses to your physical addresses. You note down at the bottom there, some of the arrows don't go anywhere. This is because the memory page is not actually in memory at the moment. Hopefully it's on the disk. How do we actually manage that mapping? Well, inside the kernel on the right hand side here we have these things called page tables, and this gives us a description for every page that the program thinks is in virtual memory, where it actually is in physical memory. And this page table also carries details of if the virtual memory page is not in memory, then where it is actually on the disk. The page tables themselves gives you this translation, and they're actually read into the processor itself, so it does the translations of virtual to physical memory. Now let's see how these components play together when we actually need to do some paging. In this case, paging in. Here we have our program running on the CPU in user mode, and so it's going to access that last virtual memory page, the one in the stack. It finds that it's not there. We can't do a translation of this and end up in physical real memory. So it invokes a page fault interrupt. That means we end up in the kernel space and we try to recover from this. The first thing we do is check, should this translation work? If it doesn't work, then the program tries to access an illegal address, in which case we have to stop the program. We may do a core dump. If it should have worked, but it doesn't work because the page is on the disk rather than in memory, then we can recover from this. The first thing we do is find a free piece of memory and allocate that to this program. Then we start up the I/O to move it from the disk into this new memory page. Then we fix up the page tables so that the translation will now work. The virtual address will get translated into the physical memory page. And then we can go back to the program and it will restart the instruction, and just by magic it actually now works. We do the translation and it picks up the data from memory. Now let's look at the opposite case of paging out. Of course, if we carry on paging in, we end up with all of memory allocated and we can't bring any more in. So something has to actually get these memory pages back out onto the disk, so we maintain this free list so we can grab them when we need to. In this case, the work is done by a kernel process called LRUD, least recently used daemon. This is looking through the page tables to find the oldest piece of memory that hasn't been used the longest. This is a good target page to push out onto the disk and put the memory page onto the free list. It does this by setting bits in the page table that get reset every time a page is actually used. Then by looking later on at these bits, it can decide which is the oldest page in memory, and that's the one that it will page out. So it's decided that this is a very old page, it hasn't been used for quite a long time. We allocate some paging space on the paging disks. Then we fix up the page table so that we know where we're going to actually put this memory page, so that if we need to page it back in, we can find it. Then we page this memory out onto the disk. Then we fix up the page table again, removing the reference to this particular page. So now the page table entry will tell us that it's on the disk but not in memory, and we can recover from that. And lastly, we put that page on the free list so that it can be reused for something else, something perhaps more urgent. We're now going to look at the 5 paging golden rules. So first of all, is paging good or bad? Well, it's well known that paging is a bad thing in a Unix system. So we try to avoid paging whenever possible by setting parameters in our applications and our middleware to make sure that we don't try to overuse our memory, as paging out onto the disk and bringing it back in takes time and slows down our machine and ruins our performance if it goes too mad. So how much can we actually cope with? Well, this depends, doesn't it? My rule of thumb is 10 pages per second per CPU. So if you had a 10 CPU logical partition, we could do 100 pages a second without really having to worry about it at all. That is sort of a noise level. Now we can do paging perhaps 10 times or 100 times more than that if we're clever. And of course, what do I mean by clever? Well, how do we live with paging? Well, can you imagine now that we need to do perhaps a few thousand I/Os because of paging. Now if we had just the one disk, perhaps that would take us 5 seconds to work through this couple of thousand IOs. If we were the unlucky programmer and our paging out or paging in was the last one on this list, then our program would literally stop for 5 seconds until that happened. And the users connected to our program would notice a 5-second glitch in waiting for the response to come back and start getting annoyed. But if we had 10 disks operating for our paging I/O, then we'd actually get through this peak in paging 10 times faster. In this case, then we'd have a glitch of a half a second, and our users may never notice that we've suddenly done a lot of paging. Now, fortunately, with modern big disk subsystems, there's a couple of things that can really help out. First of all, if our disks have write caches on them, when we actually have to page things out, we only have to get those pages as far as the cache. It will then guarantee that it will actually be written to the disk later on. That can really speed things up. And we've just announced that in the IBM machines we can now have these solid state disks. And of course they operate a couple of 100 times faster than a real disk. So we can really do some fast I/O to these new solid state disk drives. They may be a good idea for just paging if we have a system that pages a lot. Now, if we lose a paging space on a disk, we lose the disk on which it is sitting, can we survive? The answer is no. What is in the paging space should really be in memory, and a computer system where memory is completely failing will not run very long. There's a major data integrity issue here because that may actually cause corruption on your disks. The very best we can do is to kill off any process that actually has missing memory pages. If we can't get the memory back in off the disks, then there's nothing else we can do but stop the actual programs. If this happens to be a kernel process or a piece of the kernel that we swapped out, then the machine will actually halt at that point. So the message is here is to make sure that you protect your paging space. You need to either mirror it or have it under RAID 5 to make sure that you don't lose what is in effect memory pages. Now if we fill up our paging space to 100%, what happens next? Well, I'm quite an old person, and I remember reading the Unix version 7 manuals a long time ago. They were actually written by the guys that wrote Unix itself, Ritchie and Thompson, and they said that if you run out of paging space, absolute mayhem is guaranteed, and I particularly remember that phrase. If a process asks for memory and you haven't got paging space to back that up, then you cannot let that program continue, so it will have to be crashed. In the case of AIX, if it gets into this position, it actually pauses your program for something like 5 seconds and will retry getting virtual memory pages. If it can't do that, it will go through that loop a couple of times, and it's hoping that some other big process will stop and free up some virtual memory space, and so that it can allocate the space to your program. But if after a couple of loops it can't do that, it will just crash your program. It will actually just evaporate. There'll be no sign or any clue that this actually happened, because there's nothing the computer can do at that point to recover from that situation. So here are the 5 paging space golden rules. First of all, try not to do paging because it can hurt performance. If you're doing some paging, don't panic. If it's low-level paging, then we can live with that, and particularly on systems with a large amount of memory, large number of programs, and large numbers of users, they do regularly page. Sometimes there's nothing you can do about that. And what you have to do is live with it. So we're going to use lots of disks, do that paging very fast, and we can get through glitches in paging without any damage to performance. Always use protection, either mirroring at the AIX level, or we can use RAID 5 down on the disk subsystem. And never ever run out of paging space, because mayhem is the result of that. Now there is another term that we want to explain. It's called the working set, or sometimes called the resident set. Now if we have a program and it's 1 gigabyte in size, we can see here that this is 250,000 4K pages in size. We can see there are loads of pages that make up a reasonable size program. Out of that, as we said before, some of it is called the code. Kernel developers tend to call it the text of the program. Then we have the data that came as part of the program when it started up. Then we have some libraries. We'll ignore some details in there. Then we have the heap that grows as the program asks for more memory to use it as temporary working space. And we also have a stack that grows from the other end as we make function calls. Now, at any one time, only parts of the program are running. We're typically running around some loops regularly, but other parts of the program, particular functions, haven't been used for a long time. They don't need to be in memory. Some of the data, we're actually actively sorting and manipulating some data, some of it in the data, some of it in the heap space, and we're making function calls and coming back out of them, so that usually the top of the stack is pretty hot. So these pages in red are the only ones that really need to be in memory to let this program run for the next couple of seconds. And this is called the working set or the resident set, and the resident means resident in memory. And we can see these if we use the ps command or perhaps the nmon command to look for the things that look like resident text and resident data. And you can see how much of the program is actually in memory at the moment. Do be careful though, because some of these pages can be shared. For example, the code or text, they can be shared between multiple programs. So we're doing some other techniques in here to reduce the amount of memory needed in the machine. Now when we get to AMS, we'll find that AMS is working at the working set or resident set of a whole logical partition rather than the resident set of a particular program. But the same principles are involved. Which bits of the logical partition are actually needed to actually run this logical partition for the next few seconds. Let's put that another way. Here we have the AIX paging level. We have the processes on one side, they're in memory, and the least recently used daemon is paging some of those out, so it maintains the free list, pages the memory you can grab quickly, and when the program demands a page that isn't there, then we got a memory access and we pull in the stuff from the disk. At the AMS level, of course, we have lots of logical partitions. Each of those are doing paging for themselves onto their paging disks. And you may not realize it, but the page tables of all the logical partitions are actually owned by the hypervisor in our Power 4, 5 and 6 based machines. This is so that the hypervisor can make absolute guarantee that logical partitions don't look at memory that they don't own. This is how we can guarantee the security of the memory in a logical partition. So each logical partition actually makes a hypervisor call to actually update the page tables. Now, because the hypervisor owns the page tables, the hypervisor can look through the memory pages of a logical partition and decide, if it has to, which of those pages in memory are the oldest and which it may have to page out to allow it to maintain AMS paging. The hypervisor, of course, can't do paging in its own right. It's a piece of firmware. So it actually uses its friend at one of the virtual I/O servers to actually do the paging from memory into the disks attached to the virtual I/O server. Well, I hope that introduction to how paging works will set you up ready for understanding how active memory sharing works, and we'll look at that in another movie.